So now let's talk about hadrons. And these hadrons, they are the elementary particles which participate basically in strong interactions, electromagnetic interactions, and weak interactions. And and these hadrons, at the basic level, we can classify them into two categories. So we have hadrons as elementary particles, and these particles they participate in strong interactions, they participate in electromagnetic interactions, and they participate in weak interactions. And we have two categories. One is mesons, and the another category is baryons. Now, talking about these mesons are elementary particles, and their masses lie between the mass of an electron and the mass of a proton. So its mass lies between mass of electron and mass of proton, and this is the reasons that this is called as meson, and the literal meaning of meson is middle, and they have zero or integral spin. Okay, and certainly they obey Bose-Einstein statistics. And that's why we can also call them as bosons. These mesons can act as bosons. Now, the examples of these mesons are, we have pi mesons, whom we call as pions now, and we have pi plus, we have pi neutral, and the antiparticle of these pions are we have, for pi we have pi minus, and the antiparticle of pi 0 is pi 0. And the second example of the mesons is kaons, and also called as k mesons. So here we have k plus and we have k 0, and the antiparticle of k plus is k minus, and the antiparticle of k 0 is k 0. Okay, here I have to have a bar. So in the similar way of talking about, we have another category, what we call as, we call it eta mesons, and this eta is symbolized as eta, and it has an antiparticle eta bar. Now, so these mesons we can think of as three categories for these mesons as pions. So if I choose this as mesons, I have pions, I have kaons, and I have eta mesons. So this could be the basic classification, classification of these mesons. Now, talking about, let's start to talk about the pions, or we call them as pi mesons. So pions or pi mesons, and these particles, these pi mesons, were predicted by the Japanese physicist Yukawa in 1935. And while he was basically proposing the strong nuclear force that's needed for holding two nucleons together, and these nucleons are protons and neutrons that are inside the nucleus. Now, according to Yukawa, the nucleons in the nucleus interact with each other due to the exchange of these pi mesons. Thus, pi mesons were supposed to be the mediating particles between the nucleons. So we have pi mesons as mediating particles, or mediating carriers in strong nuclear force. Now, and then later on, what happened is that this pi mesons, we have pi plus and pi 0. They were identified by analyzing the photograph of a cloud chamber, and the antiparticles of this pi plus as pi minus, and the antiparticle of this pi 0 was identified. And talking about how these pi mesons or pions are produced, we have proton. If we take another proton, what we have pi plus d, and proton and neutron, here we have pi minus plus p, and proton plus gamma ray photon, we have pi neutral plus p. And talking about the properties of these pi mesons, the charge, they have a charge the same as that of the charge of electron, and its antiparticle has the same charge as that of electron. And for pi we have positive charge, and for pi negative we have the negative charge. And the charge on this pi 0, it is 0. Okay, and the mass of this pi plus that we have, and its antiparticle, which is pi minus, their masses are same, and their mass is of the order of 140 mega electron volt per c square. While as that of the mass of this pi neutral is of the order of 135 mega electron volt per c square. And talking about the spin of these particles, they have zero spin. So their spin is zero simply. So pi plus, pi minus, and pi zero, their spins are their spin independently is zero. Now all these pi mesons are unstable, and they decay to other elementary particles. So they decay to other elementary particles. And the mean life, let me represent that by tau. I don't think it's going to create some problem. So the mean life, of these pi mesons, it's nearly 2.6 times 10 to the power of minus 8 seconds. And for this is for pi plus and pi minus, and for pi zero, it's nearly 8.4 times 10 to the power of minus 17 seconds. And the modes of decay for pi positive meson and pi negative meson. So if we have pi positive, it has a 100% probability that it can decay into mu plus nu mu, and it's going to decay into E positive and nu E, and it's going to have a decay of mu positive plus nu mu plus gamma ray photon. Okay, and this will decay into pi 0 plus E positive plus nu E. And in case of pi negative, what we have is the final product is E negative plus nu mu bar. So these are the modes of decay for pi plus and pi minus. And the modes of decay for pi 0, if we take pi 0, it decays into a gamma ray photon and a gamma ray photon. So it has a 100% probability. And now the second kind of particles that we have in this category are kaons. And we also call them as K-mesons. And these were produced in pi and proton collision processes. So what we have is pi plus and a proton, and what we get is K plus K neutral bar plus proton. And this pi minus and a proton, here we have a neutral meson and lambda. And this can further decay into K plus K minus and a neutron. Now these K mesons are called strange particles. K mesons. They are called as strange particles. Strange particles. This is because they are produced in plenty and in very small time interval of the order of 10 to the power of minus 23 seconds through strong interaction. But they decay. They decay very slowly. They decay very reluctantly. That's in large time interval of the order of, so they decay for the time of the order of 10 to the power of minus 10 seconds probably through weak interactions. And another important thing about these particles, these strange particles, these K mesons, is that they are always produced in association with each other, and they are never produced independently. They are not produced separately. Now, this phenomenon is called as associated production. Associated production, and this was basically proposed by Gell-Mann. Now, talking about the properties of these K mesons, we have 4 types of these K mesons. What we have is K plus, and we have its antiparticle K minus, and we have K0, and we have its antiparticle K bar. And the next important property is that this K plus meson, it has a charge of simply the charge of electron. And for K minus, it has a charge minus 1.6 times, minus 19 coulombs. And the charge that we have on K0 and K0 bar, that charge is simply 0. And talking about the mass of this K plus meson and K minus meson, their masses are same. And so K plus is K minus. I mean, the mass of K plus is equal to mass of K minus, and it's of the order of 495.0 electron volt per c square. Thus, the charged K mesons are lighter than neutral K mesons because here we have 495 mega electron volt per c square for K plus and K minus. For K0 or K0 bar, this mass is 498.0 mega electron volt per c square. The spin of all K mesons is zero. I mean, these K mesons are unstable and they decay to other elementary particles. And talking about the mean life, I mean, the mean life of these K mesons for K plus and K minus, the life is nearly 1 times 10 to the power of minus 8 seconds, while that of K naught and K naught bar is nearly 1 times 10 to the power of minus 10 seconds. And the possible modes of talking about the modes of K mesons that we can have, the decay modes, like if we have K plus, we will have mu plus plus nu mu, and we'll have pi plus plus pi neutral, we'll have pi plus plus pi plus plus pi minus, and we'll have pi plus plus pi neutral plus pi neutral, and this K neutral is going to give us pi plus and its antiparticle pi minus. So these interactions are very simple to understand. And then we have eta mesons. Eta mesons. So eta, okay, and they are produced as say we have K minus hit the proton, and here we'll have 0 plus eta, and pi plus plus hydrogen 2 and 1 gives us proton, and an eta particle. Now, talking about the properties of these eta mesons, these eta mesons they have no charge. They have neutral charge. They don't have any charge. Okay, and the spin they don't have any spin. They have 0 spin, and the mass they have is the mass of these eta particles is nearly 547.0 mega electron volts. Eta mesons are unstable and they decay into other elementary particles. And the mean life of these eta mesons is about 8 times 10 to the power of minus 19 seconds. And the possible modes of decay for these what we call them as eta mesons. The possible modes can be written down here. We have eta can decay into gamma, and this gamma can be pi neutral plus pi neutral plus pi neutral, and we'll have pi plus pi neutral plus pi, okay, this is pi minus and pi neutral. So from here we will have pi plus and pi negative and a gamma ray photon. So this is about what we call as mesons. So we are discussing hadrons, and in hadrons we have taken mesons as a category, and we have taken up some of the fundamental properties of these mesons. Now we will go into the domain of, would like to go into the domain of baryons. And these baryons, they are the elementary particles, including the nucleons that we have inside the nucleus, like neutrons and protons. And we have hyperons here. These hyperons are hyperons. They are strange baryons. And they have these baryons have half integral spin. They obey, so their spin is half, and they obey Fermi-Dirac statistics. And that's why they are also called as fermions. Now, let's categorize these baryons, and we have baryons, and out of baryons, what we have is we have nucleons as one category, and these nucleons, they comprise of proton, neutron, and their antiparticles like neutron, proton, antineutron, and antiproton. So another category of these baryons is what's called as hyperons, and these hyperons can be classified into. These hyperons can be classified into what's called as lambda hyperons. And this lambda is it's a lambda hyperon, and its antiparticle is lambda 0 bar. And another important category is here sigma hyperons. Sigma hyperons. And in this case, what we have is we have sigma plus, and we have sigma 0, and we have sigma minus. And we have their antiparticles as sigma bar plus, and then sigma 0 bar, and sigma minus bar. And then we have another category here that's called as chi hyperons. And in this, what we have is we have chi and we have chi naught, and we have their antiparticles as chi bar and chi naught bar. And then we have omega. And we have omega hyperons. And these hyperons have a category of omega minus and its antiparticle omega bar minus. Now, talking about these nucleons, what we have, these nucleons are inside the nucleus, okay, and these the protons and neutrons inside the nucleus of an atom, they make up the nucleons, and the antiparticles of these proton and neutron, or neutron and proton. These are the antiparticles of the neutron and proton with a bar on their top. And these protons and neutrons, they are basically stable inside the nucleus. And however, if we have a free neutron, it's unstable, and the mean life of this free neutron is nearly 900 seconds, and it can decay into a proton. And talking about the other important properties of these nucleons, like this proton is a positively charged particle, and its charge is 1.6 times 10 to the power minus 19 coulombs. And neutron does not have any charge. And the mass of this proton, it is if I take on the mass of proton. It is 938 mega electron volt per c square, and the mass of the neutron is 939 mega electron volt per c square. The neutron is slightly heavier than that of proton, and they have a spin. The spin is half. The spin is 1/2 h bar, and proton is a stable particle, and does not decay into any other elementary particle. And a neutron is unstable. Its half-life is 900 seconds, and this neutron can decay into a proton and an electron and an antineutrino. So now, talking about the hyperons that we have, and the hyperons, what they are the elementary particles, and their masses are greater than that of the masses of the nucleons, and these particles are called as hyperons. I mean, all of these hyperons that we have, the set of all of these hyperons, they are all fermions. They obey Fermi-Dirac statistics. The examples that we have here for hyperons is we have lambda hyperons, and we have sigma. We have lambda hyperons, we have sigma hyperons, we have chi hyperons, and we have omega hyperons. And talking about these lambda hyperons, so going with lambda hyperons. These hyperons, they were detected in cosmic rays, detection of cosmic rays in 1947. And later on, this lambda hyperon was produced by injecting some pi mesons of energy, some pi positive mesons basically, of energy of the order of 1.5 giga electron volt in a cloud chamber containing hydrogen gas. So the reaction can be written down here. If we take, it's not pi plus, it's pi minus. So this pi minus plus hydrogen, it gives us a lambda hyperon, neutral lambda hyperon, and kaon, a neutral kaon. And the properties of this lambda hyperon is that this lambda hyperon is a neutral particle. It has zero charge, and it has an antiparticle as lambda 0 bar. And the masses of these two particles are equal, and their masses are of the order of 5.40 mega electron volt per c square. Now, the spin of this lambda hyperon is 1 by 2 h bar, and this lambda hyperon is unstable. It's not a stable particle. It's unstable, and it has a mean life. It has a mean life of the order of 2.62 times 10 to the power of minus 10 seconds. And the possible modes of decay for this lambda hyperon is we have a neutral lambda hyperon. You can have proton from it. You can have a negative meson and a neutron, a neutral meson, a proton, mu negative, and anti-mu, and can have proton plus electron plus antineutrino. Now, talking about sigma hyperons. Now we have another class as sigma hyperons, and all we have is in this category we have sigma plus and sigma minus and sigma 0, and we have their antiparticles as bar of plus, as bar of minus, as bar of neutral. What we call this as sigma hyperon. So we have the particles as sigma hyperons. And talking about some of the important properties of these particles, these sigma hyperons that we have, sigma hyperons, they have positive charge. That's E plus, and that is 1.6 times 10 to the power of minus 19 coulombs. And sigma minus, so this is for sigma plus. For sigma minus, we have minus 1.6 times 10 to the power of minus 19 coulombs. And for sigma 0, we have 0 charge. And talking about the mass, the mass of M is mass of this sigma positive, and its antiparticle, that is mass of sigma negative. Their masses, these masses are equal, and their mass is nearly 1189.4 mega electron volt per c square. And for sigma negative and its antiparticle, their masses are same and is of the order of 1197.0 mega electron volt per c square. And then we have mass of sigma neutral and its antiparticle, sigma neutral bar, that is 1192.0 mega electron volt per c square. And talking about the spin, the spin of all the sigma hyperons and their antiparticles is half. It's 1 by 2 h bar. And all sigma hyperons are unstable. They're all unstable, so they decay, and they have a mean lifetime for sigma plus, and for sigma minus they have a mean lifetime of the order of 1 times 10 to the power of minus 10 seconds, and for sigma neutral it's nearly 1 times 10 to the power of minus 19 seconds. And the possible modes the possible modes for the decay of these hyperons, sigma plus, sigma minus, and sigma 0, are, if I go with say sigma plus, here we have proton and pi 0, and neutron and pi plus, and neutron plus pi plus gamma ray photon, and lambda neutral, a positron and a neutrino, and categorizing the sigma minus. And for sigma minus we have the possible mode of decay is n and pi minus, or it can be n plus pi minus and gamma. It can be n plus mu minus plus nu mu bar, and it can be n and electron and nu e bar. And for sigma 0, what we have lambda 0 and gamma ray. Now this decay it has the maximum probability. Maximum probability. Now let's talk about chi. Let's talk about chi hyperons. Chi hyperons. And these chi hyperons are of two types. One is chi minus and chi 0. They're also known as cascade. CASCADE. They're also known as cascade, and their antiparticles are chi minus bar and chi neutral bar. And their properties, they have the charge of this chi minus and chi bar. They have a charge of an electron and positron, and this chi neutral has a charge of 0, and they have a mass, and the mass of chi minus and chi bar minus. It is of the order of they have equal masses. It's of the order of 1320.8 mega electron volt per c square. And similarly, the mass of chi 0 and chi 0 bar is of the order of 1314.0 mega electron volt per c square. Thus, the charged particle, the charged chi hyperons, you can see here, they are heavier than the neutral chi hyperons. And the spin of all these chi hyperons and their antiparticles, they have a spin of half, 1 by 2 h bar. And chi hyperons, they are unstable, and they decay to other elementary particles. And talking about their mean life, their mean life is, say, chi minus hyperon is nearly 1.6 times 10 to the power of minus 10 seconds, and the mean life of this chi neutral is of the order of 2.9 times 10 to the power of minus 10 seconds. And the possible mode of decay for these chi hyperons, possible mode of decay. For chi negative, what we have is lambda 0 and pi negative, and it has the maximum probability to occur. And we can have lambda 0 and an electron and anti-neutrino, or we can have a neutron and a negative pi meson. And in case of chi neutral, we can have lambda 0 and pi 0. It has the maximum. It has the maximum probability. It has the maximum probability to occur. And the others are proton and pi minus, proton and electron and anti-neutrino, and the other one is sigma plus and electron and anti-neutrino. Now, what we have is omega hyperons. Let's talk about omega hyperons. Omega hyperons. Okay, these omega hyperons, they are found using reaction K minus and a proton, and from here what we have is omega minus, K-on, and K neutral. And its antiparticle is it's omega negative, and its antiparticle is omega negative bar. Now, talking about their properties, they have the same properties, like their charges are same as that of charge of electron taking positive and negative. And the mass of this omega minus is equal to mass of omega minus bar, its antiparticle. They are equal, and nearly 1672 of mega electron volt per c square. And they have a spin of 3 by 2 h cross. And these omega hyperon particles, they are unstable, and they have a mean life. The mean lifetime is 8 times 10 to the power of minus 11 seconds. And the possible mode of decay of these omega negative hyperons, if I have omega negative hyperon, it can decay into lambda 0 and K minus, or chi negative plus pi neutral. And then so we can see here that the spin of these omega hyperons is simply 3 by 2 h bar. Now let me summarize it. What we have, basically, we have hadrons. Okay, from hadrons, what we get mesons, and the other side is baryons. So this is mesons. Okay, the other side here is baryons. And these mesons can be divided into 3 categories. Okay, into 3 categories, say 1, 2, and 3. What is that? That is pions. That is pions. We go with pions, and kaons, and eta mesons. And here what we have is, we have those particles. What we have pi plus, and we have pi minus, and we have pi 0. And here, in case of kaons, what we have is we have k plus and k minus, and in case of eta mesons, we have eta. Okay, so going with baryons from this side, what we have is, we can divide them into 2 categories. One is nucleons, and the another one is hyperons. Now, these nucleons, they can be divided into into protons and neutrons. And these hyperons can be divided into lambda, sigma particles, chi particles, and omega particles. Omega. This is sigma and this is chi. And from here, this sigma can be divided into sigma plus, sigma minus, and sigma neutral. They have their associated antiparticles. And talking about this chi, what we have for chi, let's go with this kind of, so for chi we have chi negative and chi neutral. So this is the classification of these hadrons that has been summarized using this notation. Now the better option here is to go with the table, because it's always better to have a table, and once we have a table, and we can have a clear look at these things. Now, what should I start with is I'll use it for mesons. So what we have is particles, their antiparticles, then the charge, then the spin, and the mass. Okay, then mean life, and the typical decay. I would like to put that in the last line. So let's go with the family here. So what I have here is I'll take a family here, and then I have a particle, and this particle has antiparticle, and it has charge in terms of E. Okay, so spin and mean life, and I think this should go with this will go with mass in terms of mega electron volt per c square, mega electron volt per c square, and then go with mean life, and finally go with some typical decay associated. Now here I choose mesons first, and in mesons what I have pi plus. It has an antiparticle pi minus. It has a +1 charge. It has 0 spin, and its mass is 140 mega electron volt per c square. Mega electron volt per c square. It has it has a mean life 2.6 times 10 to the power of -8 seconds, and its typical decay is pi plus, giving mu plus nu mu. So this is the first particle. Now choosing the second pi 0, its antiparticle pi 0 and 0 charge. It has 0 spin, its mass is 135, and it has a mean life of 8.4 times 10 to the power of -17. And the typical decay for this is a pi neutral can decay into a gamma ray photon, Okay, now this is meson. Now K plus. Its antiparticle is K minus, and it has a +1 charge, and it has 0 spin. Okay, it has a 0 spin. Its mass is 495 mega electron volt per c square. It has a mean life of 1.0 times 10 to the power of -8, and the typical decay for this is K plus gives mu plus nu mu. Okay, this is another particle. Now let's go with K neutral. Okay, so its antiparticle is K neutral bar and 0 charge. It has a spin 0, and its mass is 498, and its mean life is 1 times 10 to the power of -10. Its typical decay is K0 into pi plus pi minus. Okay. Now after this we have eta. And this eta has eta as its antiparticle, and it is having 0 charge, and it has 0 spin, and its mass is 547, and its mean life is 8 times 10 to the power of -19. And the typical decay for this is eta goes down with gamma ray photon and gamma ray photon. So now let's go with proton P. And for proton, what we have its antiparticle as P minus, and it has a +1 charge. It has a spin half, and its mass is 938 mega electron volt per c square. It is infinitely stable. And then talking about neutron, we have an anti-neutron for it, and and its charge is 0. It has a spin half, and its mass is 1115. Oh no, that's wrong. It's 939. It has been 939 mega electron volt per c square, and it has a mean life of nearly 900 seconds, and it decays like the typical decay is proton and an electron and an anti-neutrino. So proceeding from here, I don't know whether it's visible. Yeah, it is to some extent. So after neutron, let's go with lambda 0. And this lambda 0, it has an antiparticle of lambda 0 bar. It doesn't have any charge, and it has a spin half, and it has a mass of 1115. 0.40 mega electron volt per c square. It has a mean life of 2.62 times 10 to the power of minus 10, and the typical decay for this lambda is this lambda 0 goes into a proton and pi minus. Now proceeding from here, okay, so we are putting both of them here, mesons and baryons. So proceeding in the same fashion for 1, 2, 3, 4, 5, 6. So what I have is we are aware about the categories now. So we have sigma. Now we have sigma. Okay, let me choose it here. I don't know whether I'm going it. So its antiparticle is sigma plus. So it has a +1 charge. It has a spin half. It has a mass of 1189.4 mega electron volt per c square. It has a life of 1 times 10 to the power of minus 10 seconds. And the typical decay for this is sigma plus goes with proton plus pi neutral. Okay, now after this we have sigma negative. For sigma negative, its antiparticle is sigma negative bar. It's +1. Oh no, its charge is -1. So its spin is half, and it has a mass of 1192 mega electron volt per c square. It has a lifetime of 1 times 10 to the power of minus 19 seconds, and it has a typical decay. Sigma sigma minus is neutron plus pi minus. All right, then we have sigma 0. It has an antiparticle of sigma 0 bar, and charge is to be 0. It has a spin half. Its mass is 1192. Here it must be 97. It's 97. It's 1192. 1 times 10 to the power of minus 19, and it decays into lambda 0 and gamma. And then we have chi negative, and it has an antiparticle of chi negative bar. It has a charge of -1. It has a spin of half. Its mass is 1320.8, and its mean life is 1.6 times 10 to the power of minus 10. And this chi negative can typically decay into lambda neutral plus pi minus. And then we have chi 0. This chi 0, its antiparticle is chi 0 bar. It has 0 charge. It has half spin. Its mass is 1314, and its mean life is 2.9 times 10 to the power of minus 10. And it has a typical decay of lambda 0 plus pi 0. And then finally, we have gamma, and its antiparticle is gamma. It's gamma minus. It's gamma minus bar. It has a -1 charge. It has a spin of 3/2, and it has a mass of 1672. And its mean life is 8 times 10 to the power of minus 11. And it can typically decay into lambda neutral plus k minus. So with this, I would like to stop here. I'm exhausted.